My talk today is couplers. Okay. So first, I'd like to thank my collaborators. So they are the main contributors of this work. And also, I want to thank my sponsors. Okay. So coupler, uh, is originally a tool for coupling multiple scientific applications loosely. So it's known as a multi-physics coupler, so coupling the ocean atmosphere, fluid structure, etc. So they are connecting multiple applications using various grid mesh systems, such as a finite element, finite difference, like this way. So their main work is doing the interpolation and extrapolation. Complex workflows for real-time integration of scientific simulations, data assimilation analytics, and machine learning have become very common in these days. So we call this integration of S+D+L. So overall, time to solution is an important issue from the viewpoint of the performance, while optimization of each procedure is also essential. So in my project, Coupler has been extended to a tool for efficient workflow in recent 10 years. So I try to show the pathways towards the sustainability of the software through this history. Okay, so this is the history of the project and also the budget. Okay? So it started from 15 years ago, and we have 3 big projects. So in these days, so budget is based on the Japanese yen. So it's a wide range, roughly. So this 139 million yen is corresponding to $1 million. So at the current currency. Okay. So I just go through the 3 projects. So starting from the ppOpen-HPC. So I'm working for the Supercomputer Center of the University of Tokyo. So this is the history of our supercomputers in this century. So basically, we are operating 2 big systems, and each has a 6-year lifetime. So that means every 3 years, we have a new system. But you can see, so we have recently some gaps, mainly because of the delay of the development of the hardware. So we have more than 3,000 users, and it's a shared system. So therefore, more than 50% of the users are outside of the University of Tokyo. So we have several industry users and also international users. So you can see, so recently we have systems with green tags. So that means that accelerators such as the GPUs. So they are increasing now. Okay, so I start from the first project, ppOpen-HPC. So in this range, we are operating 2 types of systems. One is a commercial version of the K computers, and another one is a big Xeon Phi system. Okay? So ppOpen-HPC is a application framework with automatic tuning, AT. PP stands for the post-beta scale. It's a 5-year project supported by Japanese government from 2011 to 2015. But finally, so it has extended until 2018 under collaboration with a German project. So it's called as SPPX DFG. So we collaborate with the SX2 project led by Professor Gerhard Werein from the FAU Airlines. So this is a very nice experience. Okay? So it's a big team with 7 institutes and more than 50 people, including 5 postdocs from various kinds of the areas. So you can get the open source software from this website. So we have many development, and but we have developed a coupler called ppOpen-Math MP. So MP stands for multi-physics. So it's a weak coupling of the multiple applications. So each application does a single computation, ocean atmosphere or fluid structure. So this was originally developed as a coupler of the NICAM. It's an atmosphere simulations using a semi-unstructured mesh, and COCO, it's an ocean code for the structured mesh. So for the global climate simulation using the K computers. So it has non-centralized, fully distributed operations, no master process. So this is 15 years ago. So this kind of issue was still new thing. at that time. So we can cover the various types of meshes and grid systems. And we also extend this coupler for other purpose. Okay, so this is the original purpose for this coupler. So for the global climate simulations. And so we combine the NICAM and the COCO, and using the thousands of the nodes of the K computers, we took that 20 hours for the calculation of the 2 months. So one of the scientific findings using this system was find the mechanism of the super El Nino phenomenon. So this is a newspaper article at that time. So it's 8 years ago. So in Japanese paper. So they describe the K computer and the very scientific issues, but there are no statement about the coupler. But it's very important. We also extended this coupler for the coupling simulations of the seismic waves and the building vibrations. So building part is done by the finite element method. And so this seismic wave propagation is a finite difference method. So each code are developed by our project, and we are combining these 2 parts by our coupler. Okay, so this is the first stage of the coupler. So it's a very typical multi-physics coupler at the beginning. Okay, so next one is the H3 Open BDEC on Wisteria BDEC 01. So it's a very recent project. And so this one is a Xeon Phi system, which I mentioned before. And we introduced a new system 4 years ago, and it's still working. So it's called Wisteria BDEC 01. So in recent 10 years, so yeah, supercomputing has been changing, as you know. And we think the integration of S+D+L, so it's an initial of the simulation, data, and learning is very important. So we have various types of workloads on the supercomputers, in addition to the traditional computer science and engineering. So these are the simulations. We have a new workload and new users, such as the big data analytics, AI, and machine learning. And the integration of these 3, simulation, data, learning, we call this S+D+L. So this is very important towards Society 5.0. So this is a human-centered and safe and secure society proposed by Japanese government by integration of the cyberspace and physical space. So it's an idea of the digital twin. So we started the project called BDEC, Big Data and Extreme Computing, since 2015. So we have been developing a platform for integration of S+D+L. But in our case, we are focusing on simulation. Okay? So data and learning are supporting the simulation for the more sophisticated simulation. So Wisteria BDEC 01 is the first BDEC platform which started its operation 4 years ago. Okay? Total peak performance is 33 petaflops, and the aggregated memory bandwidth is 8.38 petabytes per second. So this system is by Fujitsu. So we have 2 types of the node groups. So one is the simulation node groups called Odyssey. So it's based on the Fujitsu's Prime HPC FX1000. So it's a commercial version of the Fugaku supercomputers. And totally, we have nearly 8,000 nodes. The peak performance is 26 petaflops. The scale of this system is 1/20, 5% of the Fugaku supercomputer. So another part is a data and learning node group called Aquarius for the data analytics and AI machine learning workload. So it consists of the 45 nodes of the Intel Xeon Ice Lake and NVIDIA A100. So Ampere. So we have 8 GPUs for each node. So that means we have totally 360 A100 graphics card. So this part are connected to the external resources directly, and we can introduce the external data from the outside of the system. So 2 node groups are connected through the InfiniBand EDR with a 2 terabyte per sec, and also the fast file system. So the bandwidth is at 1.0 terabyte per second. So this is how we utilize the system. So models and parameters for nonlinear simulations are optimized by data analytics and machine learning. So thus, we can accelerate the cycle for the parameter study for the real-world nonlinear simulations. So that's our final goal. So this is how we utilize this system. So last fiscal year, from April to last March. Okay? So we are combining these systems, but generally they are separated. Okay? So you can see Odyssey part, engineering, space science, material science, and energy physics. So it's a very traditional area of the simulations. But you can see in the case of the GPU part, we have a very different color. So we still have a 50% for engineering and simulations. And this 25% is for AI. So mainly for the experiments for the large language model. So bioinformatics is a new area, so such as a genome analysis or medical image recognition by machine learning. So this is a new users such as a University of Tokyo Hospital. Okay? So this is the hardware. And we also developed the software called H3-Open-BDEX. So it's an innovative software platform for integration of S+D+L. So it's also a 5-year project supported by Japanese government until last March. Okay, so leading PI myself, and so it's also a very successful project. So we have 3 innovations. One is the utilization of the mixed precision. So next one is the integration of the machine learning and simulation. And the third one is the software and utilities for the heterogeneous environment, such as the Wisteria BTX01. So I focus on this part. Okay. So Wisteria BTX01 is the first really heterogeneous system in the world, I believe. And we have 2 different architectures based on the different nodes. Okay. So combining these 2 parts is very difficult because a single MPI job over Odyssey and Aquarius is impossible. But fortunately, so they are connected through the InfiniBand EDR and fast file systems. So we developed the H3-Open-Sys Wait IO. So we call this Wait IO as a part of the H3-Open-BDEX. So it's a library for interprocess communication over InfiniBand EDR with MPI-like interface. And we just utilize a primitive InfiniBand library. Basically, we have 3 versions. So Wait IO socket is through the InfiniBand, and Wait IO file is through the fast file system. And the Wait IO hybrid is automatic switching between InfiniBand EDR and the fast file system. Because file size is small, so network is good. But if the size is large, so file system is rather better. Okay. So this is the interface. It's very similar to the MPI, and that provides a communication between the Odyssey and Aquarius through InfiniBand EDR. Okay. So this library can be called from Fortran, C, C++, Python, and also Julia version is under development. Okay, so I'll show you some examples. One is seismic simulations combined with real-time data assimilation. So we combine the observation from the more than 1,000 data points in Japan, and we combined these with a real-time simulation and get the very accurate solution for the computation. So this is a system. So we can get the observation data real time to this Aquarius part. So this one is doing the filtering, and we send this data to the Odyssey, and this Odyssey is doing the assimilation and the computations. And finally, results are going back to Aquarius part, and they do visualization. So this is the interface. So this part is sending the filtered data from Aquarius to Odyssey. So both codes are written in very classical Fortran. And you can see, so this part is a call wait IO MPI I send many times. And this part is just called receiving. Okay. So inside each node, we apply the MPI. But so communication between these two nodes, we call wait IO. Okay. So it's a very convenient library. So we applied this system to the Ofu Niigata 2007 earthquake. And so this is Niigata, and this is Tokyo. So it's a 200-kilometer distance. And in this area, so it's a 460-kilometer square, we have nearly 350 points for the observation. Okay, so we just utilize these data. Okay, so this is one of the examples. And so yeah, we can do this type of the simulation. We also developed a coupler called the H3 Open Util MP. And it's extended the version of the multiphysics coupler. And we have two capabilities. So one is the coupling of the simulation on Odyssey and AI on Aquarius, combined with the weight IO library I mentioned in the previous part. So this coupler is originally for the MPI-only environment in the previous section. But we extended this coupler to the heterogeneous environment combined with the weight IO library, which I mentioned before. So thus, we can easily connect the simulation part on Odyssey and so AI machine learning part on Aquarius. Okay? So I'll show you some examples utilizing that. It's a global cloud physics. So in these type of simulations, we need to combine the very high resolution model and the low resolution model. So this one is called parameterization. Okay? And you can see we need a certain amount of the computational time for this parameterization part. Okay? So our motivation is replace this part with AI. So basically, so we train by the result of the high resolution model. And the high resolution model is a NICAM in Fortran on Odyssey. And the training and inference part is a PyTorch with a 3-layer perceptron. It's a very simple model on Aquarius. And the training of AI by simulation and the simulation plus inferencing is a seamless on Odyssey and Aquarius. Okay? So this is a very preliminary result. So input is air density, internal energy, and vapor density. And we estimate the gradient in time direction of these three parameters. So this is a result of the simulations, and this is a prediction by machine learning. Okay? So generally it's good, but we still need some improvement for the capturing the peak values. Yeah. Yeah, we try to introduce some kind of the generative AI for improvement of this type of the phenomena. So another one is the special capabilities for the data assimilation and ensemble simulation for the coupler. Okay. So I believe you know about how to do the weather prediction. So in that case, we apply the ensemble-based data assimilation, where we run the 100 or 1,000 cases, and we do some data assimilation and predict the next stage. Okay, so this is a very small model, but so if you want to solve the global atmospheric simulations with a 14-kilometer meshes, you need 160 nodes of the Odyssey. Okay, and if we do 64 ensembles for 9 hours by this ensemble-based data assimilation, we need more than 2,000 node hours. Actually, so 9 hours is very small, but so we need a certain amount of the computational resources. So our proposed method is called ensemble coupling. This is an ensemble plus coupling. So this idea is a coupling the low resolution ensemble data assimilation with a high resolution simulation. So we can reduce the resources so by this way. So instead of the 64 very fine meshes, we apply the meshes with a 224 kilometers. So it's a 16 coarser mesh compared to the original. But we need to run the one fine mesh. Okay. So, but if you combine these methods and also apply the single precisions, we can reduce the total computation time from the 2000 node hours to the less than 20 node hours. So it means a performance improvement with 100 times, okay? More than 100 times. And we keep the accuracy, and the upper is the original computations, and the lower is the result using the ensemble coupling. Okay, okay, so this is a very new result. I talked about the open with IO library. So this is a very nice library, so which combines any types of the CPUs and the GPUs and the other devices, such as the AI chips or quantum computers. Okay, so I skip this part. So recently, we started a new project, QC-HPC hybrid computing. QC is a quantum computer. So it's called JHPC-quantum, also supported by Japanese government. And the RIKEN, SoftBank, and University of Tokyo and Osaka University are participating. And this project has a strong focus on the industrial applications. And we are introducing two real quantum computers. And one is IBM's most recent Heron system with a 156 qubit. And another one is a continuous ion trap system with 20 qubits. So continuum system has already started to operate in this February. So target applications are quantum sciences and quantum machine learning. So role of the University of Tokyo is research and development of the system software for QC-HPC hybrid environment, where we treat the quantum computers as accelerators. Okay. So this is the extension of the H3 Open VDEC, as I mentioned in the previous part. Fugaku and Miyabi and Wisteria VDEC, so they are our systems, will be connected to quantum computers in March 2026 or before. So our current plan is starting the hybrid service from this October. Okay. Okay, so this is our current project. And basically, we are now extending the weight IO library for the Python interface because the Python is very popular in the quantum computers. And also, we are developing the weight IO router. So it's a communication library among supercomputer centers over SciNet. So SciNet is a Japanese academic network. So last fiscal year is a simulator on the Wisteria VDEC01. But we are now moving this method to the real QC-HPC environment. And also we are developing the weight IO for Julia. Okay. So this is a weight IO for Python. It's a sample code. And also, so this is a very brief overview of the weight IO router for center-wide communications. So through SciNet 6. Okay. So the original weight IO is for the heterogeneous supercomputer system between the CPU and GPU, but now it's extending to the wide range network. So last fiscal year, we developed a simulator of the QC-HPC hybrid environment on our Wisteria VDEC01. So where we treat Wisteria VDEC01 Odyssey as a supercomputers and Aquarius as a quantum computer. So we installed NVIDIA's CUDA-Q, which is a quantum simulator developed by NVIDIA. And so it's now available on Aquarius. So we held a one-day tutorial last year, December, was a QC-HPC hybrid with CUDA-Q plus Wisteria BDEC01 and H3 Open BDEC. Okay, so this is a schedule for the tutorial. So we start from the 10 o'clock. And the morning is mainly for the very introduction for the CUDA-Q and quantum computers, and also the log into the BDEC system. And afternoon, so we apply some very introduction for the VQE, variational quantum eigensolver. It's our target application for this tutorial. And finally, we experience the QC-HPC hybrid using this system. So this is a very simplified version of the VQE. And so I just skip the details. And basically, so we try to get the ground state. So it's corresponding to the minimum energy, which is a minimum eigenvalue. Okay. And we are doing the separate calculations on the Aquarius and Odyssey for this VQE part. So this is algorithms for the variational quantum eigensolver VQE. And so the main computation part is by Odyssey, and the sampling part is done by Aquarius. So this part is good for the quantum computers. So we need to repeat this system. Okay, so this is a hybrid system on Wisteria BDEC01. So this is an interface between Odyssey part and Aquarius part. And this is a Python script. So sorry, some Japanese language are included. But we are doing so. These are the functions for the wait IO. Okay. And this is a job script. So we need to submit the two separate job scripts. So we have some rules for the common computations. And if they grab the resources simultaneously, we can start the job. So this is the result for the very simple hydrogen case using just 4 qubits. And you can see solution is converging to the accurate solutions. Yeah, we have compared several interfaces such as wait IO hybrid or wait IO socket, but mainly they are very similar because the data size is very small. Okay. Okay, so I just go through the history of my Kepler and how that evolved. We start with the MPI-based Kepler, so for the atmosphere and ocean, and also apply to the applications. So next one is a heterogeneous environment, and combined with the wait IO and the real-time integration of the S+D+L and ensemble coupling. So we extended this idea to the very wide range of the applications. And the most recent application is a QC-HPC hybrid, and the further development of the wait IO, such as other language interface, and also wait IO router, so which is still under development for center-wide communications. Sustainability of the software of the such as the Kepler is very important. And so to be honest, it strongly depends on the continuous funding. But extensions of the target applications and systems with additional developments for the adaptation, such as wait IO, so they are very important. So Kepler is a very important workflow tools towards the AI for science now. So those involved must always keep their eyes open and pay attention to whether it can be applied somewhere. So that's what I learned in recent 15 years. Okay. Okay. So this is just our history. Okay. So thank you very much for your attention. And I have one slide, and I'm one of the organizers of the Supercomputing Asia and HPC Asia 2026 in Osaka, January next year. So Rio is also the co-organizer with this conference. And the paper submission due is early September. And so please submit your works. Okay. So thank you very much for your attention.
All right. Thank you very much, Kengo, for the very wide and broad coverage of the 15 years of work that you have done. So the attendees can post questions on the Q&A. I think you can also raise your hand. I actually don't know how I could turn on the mic for the normal participants, but yeah, so maybe I could ask a couple of questions about the coupler. So when you couple these simulations and then you need to obviously communicate some data between them, is the communication the bottleneck when you have like strongly coupled simulations or data simulation? Is the communication very heavy in the coupler?
Yeah, it's a good question. And it depends on the applications.
Mm,
And so generally speaking, for example, in the case of the atmosphere and the ocean coupling, so they just exchange the data on the surface. Okay? So it's very smaller compared to the computation.
mm,
And I think the bandwidth is not the big problem, so but rather latency yeah,
mm.
could be the so larger problem. But
I
generally
see.
speaking, so yeah, sometimes the communication might be so very uh, big overhead. But we have many types of the some remedy. For example, so coupling the so overlapping the communications and computations technique, and we can hide so such kind of the communication.
I see. I see.
Mm.
Well, yeah, I understand that it's very case dependent.
Mm.
Um, okay, so I think I can now allow people to turn on their mic. If you raise your hand, I can actually
You,
turn on your
Rio, do
mic.
you see the questions in the Q&A
Yeah,
box?
yes, I see them too. I'm
Okay,
just
great.
announcing the capability to, yeah, if you raise your hand, I can turn on your mic, but we also have a few questions in the chat, the Q&A chat window. So let me read those questions. The first one is, for the hybrid HPC quantum calculations, does it require co-location of the HPC and quantum computers? What are the requirements in terms of bandwidth latency between the two computers? So this is a question
Okay.
about the quantum. Yes.
Okay. So yeah, it's a very challenging part. And in our case, we don't require the so quantum and supercomputers should be on the same place. So for example, we try to connect our supercomputers in Tokyo area with a quantum computer in Kobe. So it's a 500-kilometer distance. So one of the issue is security. Okay.
Mm,
So yeah, both of the so uh, systems and also the site has a so each year own security policy. Okay. So generally speaking, in the case of the university, it's not so strict, but RIKEN, so it's more strict.
yes.
Yeah, we just start discussing to access from Tokyo to Kobe yesterday. Okay, and we still have so many issues. But so one important point is that security. So it's not so technical, but so security is an important issue. And of course, the bandwidth and latency is a big problem. And I think that latency is a bigger problem. And of course, we use a public network between the two sites. So therefore, it depends on the traffic condition. So sometimes it could be very slow. But we need to do that. Okay. And, so we try to combine the direct network communication and also some kind of the cloud file system, through the cloud file system. Yeah,
Okay.
so that's one remedy, I think.
Yep. Yeah, we have a few more questions in the Q&A window. Let me pick up one question from the Q&A, and then there's also a hand raised, so I'll move to the actual hand raised after I read the next question. So in the Q&A, it says, it appears that some of these coupled models have a very different time and space scale. What kind of transfer operations are involved in converting the data for suitable use, and how does that affect performance?
Okay, so it's a good question, and it's a little bit difficult to answer. So basically, it depends on the applications. And I think, for example, ocean and atmosphere case, so it's a strongly coupled, but they have a very different time scale. And I'm not familiar with the details, but so generally speaking, ocean part is a longer time steps. So I think they exchange the data not so frequently. And for example, so 10 times for the atmosphere, so once for the ocean, like this way. So we can, I don't know the details about how to interpret the results, but probably they average the calculation result from the atmospheric side for the 10 time steps, and they generate the input to the ocean. Yeah, one of the examples. So, yeah, it depends on the application, but our coupler can handle that type of the different time steps.
Okay, so I see a hand raised, so I don't want this person to wait too much, so I'll turn on the mic. Hello, can
Yes,
you?
hello?
Yes, we can hear you.
Oh, excellent. Hi, Kengo.
Oh, hi, Clem.
I want to ask for the examples that you gave where you have ensemble coupling, how much effort does it take on the application side to modify it from just pure simulation to something with simulation plus the AI parameterization, something like that? How long does that take? Is it a big effort? Thank you.
You are
Yes.
this part, okay? Okay, so I don't know the exact hours for training this part, but we need to do the certain amount of the simulations using the high resolution model. Okay. So
Right.
it depends on the number of the cases.
Okay.
But it's not one or two. So yeah, therefore usually we need to do the roughly 100 cases to train the small part.
And to change the original, did the users have to change their original application to become AI plus simulation? Or this is a
repeat again?
brand new application?
Yes. So, yeah, I understand your question is so how easy to develop this type of AI simulation coupling. Does it make sense?
Yes.
Okay, so unfortunately, it's not so easy. So because our coupler is a very preliminary. And for example, so I showed the extension from the ocean atmosphere to the seismic simulations. So even in that case, we took 3 or 4 months. And this one is a very special case. And so, yeah, it's a very special code for these simulations. Yeah, actually, so we need more these type of applications to extend our coupler for general use. So it's under development. So if you want to apply your application to our coupler, yeah, it takes a while. So roughly 1 month or something. And actually, we are now going to apply this type of simulation AI coupling for the case of the blood simulation, blood flow simulation. And so, yeah, we need to see what's happening. But in the case of for example, QC-HPC coupling, yeah, it's a very easy. But this one is a not so easy part.
Okay, thank you.
Okay, I see another hand raised. This Manuel, I'm turning on the mic. You also asked a question in the Q&A, but maybe you can ask directly.
Okay. Yeah. Can you hear me?
Yes.
Okay, cool. I actually had a question on the same slide. I'm coming from a more system design perspective, so I'm an electrical engineer, and I'm looking at this app. It's really helpful to have application knowledge. I'm not very familiar with the cloud application physics, but I was curious if you could elaborate on the high resolution versus low resolution modeling, particularly about the computational resolution involved in that, and or if there's model differences between the two. I don't.
Kengo, can you?
Okay,
Yeah.
so
Yep.
yeah, basically, so they are using the same, solving the same equations, but
Okay.
it's just a calculation for the parameter. Okay,
Uh,
and so yeah, they don't need a very accurate solution in this case, but so they need some estimation for this part.
are we talking maybe, 32 bits in the high resolution and only 8 bits in the low one? With computational performance on some of that scale, or
Computational performance.
yeah,
So
precision, the numerical
precision is the same. Precision is same in this case.
Okay.
Mm.
So what then is the difference between the two models then? Maybe I don't understand the application.
So just for this mesh size.
Okay.
Like,
Okay. And then the other one, the questions I had in the dialogue, real quick, hopefully it's quick, easy, is related to the performance of using couplers. What kind of gains can you expect, and what are the optimal conditions for the use of couplers as you presented? And that's all I have.
so do you mean the coupling the simulation and AI?
Well, I'm assuming you're doing couplers to solve some kind of problem to improve performance, where you're using distributed
Yes,
computing.
yes.
So
So
what does it buy you?
okay, so in the original case, anyway, so we need coupler between the high resolution model and low resolution model. But in this case, it's combined with simulations and the AI part. And so in this case, inference time is very small and it's almost negligible. And the computation time is, so this 25% disappeared. So performance improvement is not so significant, 1.33 or something like that. But so we have certain improvement for the performance.
Thank you.
Does it answer your question?
Yeah, this is good. Thank you. Thank you.
Okay. So, yeah, I see a few more questions on the Q&A. Maybe I can take, one more question from the Q&A in the interest of time. Yeah, I think Kengo, it's very late in Japan for Kengo and also
It's
me.
okay.
So okay. Let's see. There's one question that asks, does the existence of a coupler discourage code developers from porting their codes to more efficient processors like CPUs to GPUs or GPUs to quantum computers?
Existence of coupler discourages.
Yeah. Can you see the Q&A?
Yeah, I can see that. But I cannot get the point. How do you mean by discouraging?
Yeah, because if they can just keep their code on the CPU and couple it, maybe they are not motivated to port it to GPUs. Maybe.
Okay.
Maybe that's what it means. They can just couple instead of porting.
Okay. So actually, our system is not just for the heterogeneous part. So we can also couple the different code on same CPU. And so I think the porting and coupling is a very different thing because many of the AI applications are developed on the GPU part. But on the other hand, so many of the traditional applications are still on multi-core cluster. So in that case, this kind of the coupler is very convenient. So we have two or multiple different applications developed by different architectures. So in this case, coupler is very nice.
Right.
And
so
I don't. Okay.
I think the coupler is coupling two different applications, not necessarily two different hardware. It can be the same hardware.
Right.
Coupling two applications. Yeah.
Right.
Right. Okay. Do we still have time for one more question, maybe? I could read one more. The coupler you mentioned is to couple computations on different infrastructures. I assume you run programs for CPUs only on Odyssey and those for GPUs on Aquarius. Component models of the Earth systems have been developed to accelerate with rewriting the codes with combined CPU/GPU. How to build the coupling among this kind of Earth system models on the kind of heterogeneous machine you proposed? So maybe this is like the opposite question of the previous one.
Okay, so yeah, this is what we are seeking. Okay, so if you have this kind of the applications, yeah, we'd like to apply our code, okay, our tools, okay. But what is the questions? Yeah, it's possible, I think.
Mm-hmm. Right, so this one is asking about, yeah, actually heterogeneous hardware.
Yeah, our
Okay.
tool can so combine yeah, any type of the hardware, I believe.
Mm-hmm.
So as long as we have other solve the security problem, even for
Right.
the external system.